Okay, so we are live now to the YouTube as well. All right. So Dijkstra's shortest path. So far, we've been talking about graphs, and we're still going to keep talking about graphs. And we looked at last time at depth first search, right, and breadth first search, and how the concept of basically traversing a graph. And before that, we talked about different terminologies for a graph. Well, we talked about adjacency matrices and adjacency lists. And then we talked about terminology of the graph, and particularly I mentioned the keyword path, right? And so I said the length of the path is basically the number of edges of the path. And then we basically said that paths would come in interesting and relevant because of things like Google Maps and trying to basically be able to find out what the fastest way is to traverse a graph. Now, when it's an unweighted graph, it doesn't really matter, because with an unweighted graph, it's just the number of edges you have to go through, but each edge is kind of given the same amount of weight, basically. It's unweighted. Whereas with a weighted graph, it matters, right? So in the most basic example, if I say there's a graph with 4 vertices, and it's undirected, although this will work with directed, but we're going to do with a non-directed approach. And so if we have something like this, and then I tell you, okay, this edge weights 3, and this edge weights 10, and this edge weights 1, and this edge weights 1 as well. And I tell you, this is your starting point, and this is your finishing point. And I say, okay, which path do you want to take? Do you want to take the path through the top, so through the blue vertex or node, or do you want to take the path through the bottom or the orange vertex or node? And then the way you would decide that is which way is fastest to get there. And so on the top here, if we take this path, we have to go through this edge and then through this edge. And what we do is, to compute the length that path takes, is we add all of the weights together, right? So we say 3 plus 1 is equal to 4. So it takes 4 units per se to get from start to finish going through the blue one. On the bottom, it takes 11 because you do 10 plus 1. So assuming that the smaller the number of units, the faster something is, then the top one is a clear winner for a faster way to get from start to end. And so that's basically the concept of shortest path. How can we come up with an algorithm that can compute this between a starting point and an end node, and basically say, okay, what's the best way? Here we can see it because we just computed both of them, basically all possible paths, we computed them, and we picked the smallest one, right? But if this is a really, really, really complicated graph, trying to do that is not easy to keep track of, because the most obvious path may not be the shortest. Like, you could have something like this too. So suppose you had something where this was a 10, this is a 1, and then this is a 3. So the shortest path actually takes 2 edges to go through, because that's a length of 4. And this one, even though it's one direct edge, it takes 10. So this is like, do you want to take the highway at rush hour, or do you want to take the side streets that a lot of people don't know about, kind of thing? Sure, it's like not, there's a lot more turns and things like that than just like a straight line, but it might be faster. And that's another thing. So I'm talking about these numbers, but I don't associate a unit to them, right? That's usually how it goes, because that will depend on what you're trying to do. But most of the time, if you think about maps, that's going to be a unit of time, so such as seconds, minutes, hours, whatever. Or it could also be a unit in terms of distance, so like miles, or kilometers, or meters, and whatnot. Okay? And so ultimately, we're not thinking of a unit when we're thinking about this. But if it makes it easier for you, just think in your back of your mind as something to do. Just be like, oh, well, this is in seconds, just so it makes sense why the smaller number is better, because it's less seconds. It's faster. Okay? What about road tolls? That will be something that you would build into your graph. So like, the top, there might be tolls here, but we're including that into the 10. We're adding the toll time per se to the 10. We're including that. So ultimately, again, you want to abstract this to just think about a unit, but if it makes it easier, just associate a unit to that. All right, okay. So now that we understand that, let's go ahead and just do the algorithm and how we can achieve this. So the algorithm is not fast, okay? Let's just start out with that. Dijkstra's shortest path takes a while to compute. In fact, I have a b squared there, but I believe it's actually cubed. It should be a cube. Let me just triple check that. Oh, I guess it's putting it as square. Okay, fine. I'll trust it. Yeah, okay. Yeah, I can see why that's the case. Basically, if you think of the adjacency matrix of this, it's basically saying you got to run through every single combination in there of this to be able to find out what the smallest one is. So, okay, understandable. Oh, squared, I guess. Okay. Yeah. All right. So let me go ahead and put a graph here. And then let us go ahead and compute the shortest path for this. Now, there's two ways that I'm going to show you this algorithm. I'm going to show it to you sort of graphically so that you understand how it works. And then when I finish doing that, then I'm going to show you more of like a table version of it, which makes it easier to actually program. So when you're actually wanting to program Dijkstra's shortest path, you kind of have a good idea of what data structures you need to code, which is just a table. It's going to be a lot like the depth first search, where you have a little visited array and those kind of things. So we're not reinventing the wheel here, but there is something very cool about this algorithm that we don't typically do in this class, and that's dynamic programming. So dynamic programming is one of the sort of paradigms to program, and how you solve a problem, right? You have things like divide and conquer, and if you look at the bonus video that I said, because we won't have class that last day on Wednesday next week. But if you look at the bonus video, I talk about that stuff, so you can check it out. But ultimately, we're using a completely different approach to solving this than some of the other algorithms we've done, like sorting. And the cool thing about dynamic programming is that you save work by remembering steps. So from the most basic thing, think about like Fibonacci. So when you're doing Fibonacci recursively, it's very inefficient, because if you're trying to compute the fifth number, you got to recompute all the numbers before that. And then if I say compute the next number after that, again, you got to recompute everything before that. And you're not really saving any work. And so by remembering what the answer to something was already in the process that is known as minimization, I don't know if I spelled that correctly, but it's something like that. I do have a link on that, and I did talk about that at some point earlier in the semester, but I do have a link on Canvas for that. If you do that, then you're basically remembering. And that's the heart of dynamic programming, is that you want to remember work you've done already, so you don't do it again, because it's pointless to do it again because you've already done it. So you've done that work, so you should remember it. And so that's just the bare bones of dynamic programming. Just remember the work you've done. And how do you do that in practice? You typically do some kind of table where you store results to previous computations. And Dijkstra, the way that it becomes a good algorithm for this problem of shortest path is by using dynamic programming. Okay, so you get to see how that works as I do this. All right, so here we have a graph, and it's going to be a weighted graph, so I'm going to put in a couple of weights in here. And what I want to do is compute the shortest path between a source node and something else. However, it turns out that when you do Dijkstra, I mean, I don't know if this is a good thing or a bad thing, but it's just kind of the thing that it does. It's a feature, not a bug. Is Dijkstra, you have to start with a source node. So you have to start with your start, per se, like your starting node. And then from there, Dijkstra will compute the shortest path, not just to whatever you want, to the destination, but to all the nodes in the graph. So, that's good, I suppose. If right now you're like, oh, well, I need to compute like the shortest path to my destination here. All right, run Dijkstra. But guess what? Dijkstra is also going to give you the shortest path to here. So if you need that in the future, I guess you have that. So that's kind of nice. But also, on one side, you're like, oh, that feels inefficient. But it's just Dijkstra needs to know the shortest path to all nodes to be able to be sure that it gives you the shortest path to the node that you want. And if that doesn't initially make sense, think about it for a second. Like, let's say that the shortest path here is going to be here. You might think that's the shortest path. But unless you know, but then you also see that there's an edge here of 1. So like, you got to find out what the shortest path to this node is, because if that shortest path, let's see what the shortest path is on the top line. The path there is a 2 plus 1 plus 8. That's 11, right? And so here we have a path of a distance of 1 between those two. So if there's a path that takes less than 10 and gets us to 4 in less than 10, then that's actually a faster path, right? And I didn't put this edge, but I put it as a 4 there. But, you know, it turns out that if you actually do go this way, it's the same distance. So it's not necessarily faster, but it's the same. But there is another edge or way that you can get there faster. If you go this zigzag way here, or actually better yet, if you go this way, then it's just a 2 plus 1 plus 2, which is less than 11. In fact, it's going to be 5, right? So 5 plus 1 is 6, so the final distance that way is 6. So you can see that to be able to guarantee that you actually have the shortest path, you need to look at the other nodes around it. And so those nodes, to guarantee that you have the shortest path to those nodes, you have to look around those as well. And so ultimately this just kind of is like a chain reaction effect, where you basically have to compute the shortest path to every single node to guarantee that you have really the shortest path overall to your objective, okay? So hopefully that gives you justification as to why, and that's part of what you do. All right, so the way we're going to do this algorithm is we are going to keep track of a couple of things. And again, I'm going to do it first sort of visually here by paper, how you can do it on a test. And then I'm going to show you the table version of it. But if I show you the table version initially, it's harder to understand why it works. So that's why I prefer this method first. But you know, for some people this will be better. The other one's going to be better. So hopefully we appeal to all of you by the end of this. Can't please everybody kind of thing. So we got to do different approaches. Okay. So the way the algorithm works is going to be like the traversals, where you're going to keep track of what you visited. So that's going to be the first thing you got to remember is what you visited. Okay. Second to that is you're going to keep track of like ongoing weight computations. So what I'm going to keep track is some sort of weight, and then who my parent is, and whether or not if I've been visited or not. Okay. Now, what do I mean by parent? What I mean by parent is that whenever I'm trying to say that this node takes this much distance or unit to get there, I want to know what the route is, because not only am I trying to say, okay, what's the smallest route between the start and the end, I want to know what that route is. And so to be able to know what that route is at the end of this, I need to keep track of like what the route was done to take there, you know? I might say like, oh, well, you know, after doing my fancy computations, I have figured out that the fastest route, the shortest path is a distance of 6 to get to node 6. Cool. Which way did you go? Did you go through here? Did you go through here? Like, where did you go? So that is why you have to keep track of the path, so that you know. It's like as you're exploring, you leave a bed of breadcrumbs. You leave a trail of breadcrumbs behind you, so you know which way you came. And that's kind of how the algorithm works, okay? So we're going to keep track of those 3 things. So when we start, the first node that we're going to look at is going to be our source. So we are going to mark that as visited, okay? And so for now, since we're doing it visually, I'm just going to color it in. So I'm going to color in gray all the nodes that I have marked as visited, okay? All right, so from there, I'm going to go ahead and see all of the edges that are connected. So remember with depth first search and breadth first search, when we were visiting a node, we looked at all the outgoing edges, or, well, since it's undirected, you know, it doesn't matter. But if it was directed, we would just look at the outgoing edges. That's kind of what we're doing here. We have to go through each one and do some processing with each one. It's not going to be that simple process of like, you know, check if it's visited and then add to the queue or stack and then, mark it and whatnot. It's different here. What we're going to be doing here is we're going to be looking at each of the edges. And do notice that I put this with numbers, okay? The reason I put it with numbers and not letters is because I want you to get used to it being numbers, because when you're coding this for like CSVO or whatever, you're going to be using numbers because you have to identify the vertices by a unique identifier. So it's easier just to kind of get comfortable with that. Okay, so in this case, we have two edges that are basically going out of 0. And that's the 0 to 3 edge and the 0 to 1 edge, okay? So what we're going to do is we are going to update what the fastest way to get to those two vertex are. Initially, we make the assumption that all vertices take an infinity amount of time to get there, okay? So I can even go ahead and put in here infinity for all of them. In addition to that, they have no parent. So sad. Okay, they have no parent. And so because they have no parent, they I'm just filling in with a question mark or whatever, okay? So as we go and look at the two edges that are part of 0, we see the edge 0 to 3. And so what we're going to do is we're going to ask ourselves, okay, compare the current fastest or smallest weight that we have on vertex 3 and see if the edge that's coming out plus any addition to those, which will make sense in a little bit, is smaller than what we have. So essentially we're comparing 2 and infinity. Which number is smaller? Well, 2 is definitely smaller than infinity. So what that means is that we have found a new vertex, we have found a new path through a different vertex that is better than the one we have. And of course, anything is better than infinity. So what I'm going to do here is I'm going to go ahead and put a 2, and I'm going to put the parent. So I'm going to say, well, I came through the 0 vertex, so I'm going to put 0 there. And that's what you're going to do for all vertices, basically, okay? This process is known as relaxation. So when you find actually a better path than what you currently have, which technically anything is better than infinity, we say that we are relaxing the node. So you have to relax, okay? Dr. Guala likes doing the relax thing, so it got stuck in my head. It's pretty cool. He does it better. All right, so the next thing is we are looking at vertex 0 and 1, and we have the edge of 4 there, okay? So what we're going to compare is we're going to compare 4 and infinity. Obviously, 4 is smaller than infinity, so we have found a new path. So we're going to perform the relaxation. So here we're going to say weight of 4, and who is the parent? 0. 0 is the parent, okay? And when we finish that, then, like I said, we mark 0 as visited. We don't mark the other 2 as visited. We don't need to add them to anything. We keep track of that ahead. I guess we could add them kind of like how we added to the visited list and whatnot, but don't think about that for now. Again, I will show you those specifics once we do the table version of this. Okay, so now that we have this, we have to pick another vertex to work with. So whereas with the stack and queue, with the def first search, ref first search, we have our stack and queue to tell us what to pick next. Here, what you have to do is you have to look at all of the remaining vertices that are not visited. So technically, pretty much all of them except 0. And pick the one with the smallest weight associated to it. So like this number. Of course, the infinity ones are not even something to consider. So we really have 4 and 2. So we're just going to pick 2 because that's smallest. If you had 2 of them that were basically the same weight, so like let's say the both of these were 2 of weight, then it doesn't matter which one you pick. You can pick either one. It does matter. It does. What you should think about though is when that happens, if this is part of your final path, then that's telling you that there may be more than one solution to the shortest path problem, which can happen when there's 2 paths that take the same amount of time and both are the fastest. Okay, so something to think about as well. Okay, so that means that we are going to be working with vertex 3. So first of all, we mark it as visited. And now we're going to look at all the edges coming out of that vertex, and we're going to do the same thing. So let's just start with vertex 5. So we have edge going from 3 to 5. And so we need to compare the running weight with what we currently have. So this is where it gets a little tricky. And this is so next class, we're going to learn minimum spanning trees. And the tiny change that I'm going to do here, one of the algorithms that we're learning next week is almost identical to Dijkstra, with one exception. And the exception is what I'm about to do now. So it's just something to keep in the back of your mind over while you're eating turkey later in the week, but or vegetarian option if you're into that. But when we come back next week, you'll see that we're going to revisit this algorithm, and we're going to make this tiny modification, and all of a sudden it's a minimum spanning tree algorithm. So, and that modification is that instead of comparing 1 and infinity here, what I need to do is I'm going to literally compare. I'm going to take the number that I have here from the 3, that's a 2. I'm going to add this weight to it, which is the 1, that's equal to 3, and then 3 is what I'm comparing with infinity. The reason why is because you want to compare not just the weight of the edge that you're using to look at, which is the edge from 3 to 5, but you also want to add how long it took you to get there, because ultimately you're trying to compute the shortest path to your destination, right? And that's basically the addition of all of the edges that took you to get there. So that's what we're also adding the 2. So hopefully that makes sense. So again, we're comparing 3 and infinity and not 1 and infinity because we don't just care about how much time it takes us to go from 3 to 5, but also how long it took us to get to 3 in the first place, right? It doesn't matter if, like, imagine this, when you're doing Google Maps, you know, you're trying to figure out the fastest route is, and you know that once you get to like the UNLV parking, you know, from there to your class, it takes you 5 minutes. Okay, cool, but that's not the total time it takes you to get there, because you actually have to go to the parking first, and from your house to get to the parking is a completely different story, right? So you have to add that time in together, and that's the difference. With minimum spanning tree, we're only looking at the 1, and we compare that with the infinity. So we'll come back to that, but just something to keep in mind, not just for you, but also when you're taking a test, to not confuse the 2 algorithms together, because it's possible. Yes, I used to eat tamales, but I don't eat them anymore because I'm trying to be diet-like, and they're very high calorie content. But I do like the candy ones, the pink ones. All right. Okay. So because of that, we still have 3 being less than infinity. So we are gonna put that in here. So 3, and then we're gonna put the source of that, which is no 3. Now that's very easy to confuse. So hopefully we don't confuse which numbers which later. Okay, that's one of the paths. The other one that we need to look at is 2. This one's going to get updated 2 because, I mean, this is infinity, so anything is better than infinity. But we don't put 3 here because we need to add the 2, right? So we need to say 3 plus 2 is 5, and then we say that comes from 3. Okay, so again, you got to make sure you add the numbers together. Don't just put the weight of the incoming edge here. Okay, so that takes care of basically, here I'll highlight them so you know which ones we looked at. So that takes care of those 2 edges, and we also did these 2 earlier. And now you might consider, what about looking at this edge again, right? Because, I mean, after all, that is technically coming out of 3 because it's undirected graph. Well, you don't need to worry about it because you don't need to update any edges from things that are already visited. So remember, just like depth first search and breadth first search, when something's already marked as visited, you kind of say it's done at that point. So no need to worry about updating that edge at all. And that's good because, I mean, that would probably break the code if we try to. Okay. Also, I guess if you're really pedantic, technically this has a weight of 0 because you're starting at 0, and it has no parent because that's a start. So just remember that's the start. Okay. All right. So now we have 5, 3 here. We have 4, 0 here, and we have 3, 3, right? So we have a weight of 5, a weight of 4, and a weight of 3. So to pick the next node to visit is we are going to pick the smallest weight. So that is going to be this one. All right, so this one, we have technically 4 edges to look at, but one of them we don't care about because it's already done, that one. So we have the edge going from 5 to 2, 5 to 4, and 5 to 6. So it doesn't matter which one we look at first. So I'm going to go with the easy ones. I'm going to go with these two first because they're going to be updated, because right now they're set to infinity. So anything is better than infinity. So there we go. How much though? So we're going to take this value here, and we're going to add to that the edge to it. So it's going to be 3 plus 2 for this one, and this one's going to be 3 plus 8. Right, so 3 plus 2 is 5, so we're going to put in here 5 with a parent of vertex 5. That's so weird that the numbers keep matching, like 3, 3, and 5, 5. That's just like it wants us to be confused. And then over here, I'm going to erase these so you don't get confused, but that's 3 plus 2. And then 3 plus 8, which is going to be 11, and that one is coming from vertex 5. Okay? So now the interesting edge, which is the edge going from 5 to 2. Right, so 5 to 2, this is technically going to be 3 plus 3, which is equal to 6. However, 6 is not less than 5, right? So because 6 is not less than 5, basically you don't need to update the edge going this current data here. Why not? Because if we did update it, we would have put a 6, 5. So what that would be saying is that the shortest path is through vertex 5, and it takes a distance of 6 to get there. But that's not the shortest path, because there is a better path that goes from vertex through vertex 3 that takes currently 5. So because that's better than what we have, then we don't update it. So nothing happens there. There's no update done. Okay, so that's the check that you do. Don't worry, I have this like a little mini algorithm I'm going to copy and paste from my notes so you can remember all these things when I do the table version. Okay, that means we looked at this and we are done with it. So now, again, we're going to run the algorithm back here and see what we can do. So we got 5 here, a 4, a 5, and an 11. The smallest number here is the 4. So that's the one that we're going to work with here. Okay, so that one has 2 edges to look at because this edge is already taken care of. So we have this edge, so let's start with this edge. So for this edge, we would have to do 4 plus 10, which is 14. 14 is definitely bigger than 5, so that means it's not efficient, so we don't update this data here. Cool. This one, let's see. Well, this one we got 4 plus 6. That's 10. That's definitely not less than 5. So that, again, that one does not get relaxed. That's the correct terminology. It does not get relaxed. Okay? All right. Cool. We have 3 vertex left with values 5, 5, 11. Okay, 5, 5, 11. So that means that now it's come to a situation where we have 2 vertex we could pick. And depending on which of the 2 we pick, is basically going to be like what potentially 2 answers could exist for this graph. Potentially. They might still get updated later, but it's just saying it's a potential. Okay? So in this case, I am just going to go ahead and pick this one. No, well, I have a reason internally, but technically the algorithm has no reason to pick that first. The reason I picked it is because everything else is already visited, so I have to do nothing now. It's like, yay, I'm done. Okay, moving on. Right? Because, I mean, all the 3 edges are going to visited vertices, so there's no need to update any of them. So it's like a freebie. You get a free pass. So that's kind of why I picked that first. But now we have 5 and 11, so we got to pick the other 5. This one we have to do a little bit of work because we do have this edge to look at. So we got the edge from 4 to 6. So this is 5 plus 1. 5 plus 1 is equal to 6. 6 is indeed less than 11. That means that we have found a new shortest path going into vertex 6. So we're going to perform relaxation. So that means we get rid of this. We replace it with the new lower weight. And we get rid of this. And we replace it with the new parent, which is parent vertex 4. Okay? So after we do that relaxation, then we see what else is left, but all the other edges are good to go because that's already set and that's already set. So we can say we're done with that vertex. We only have 1 vertex left, which is 6. tiny optimization on this algorithm is that you always will have nothing left to do when you're looking at the last vertex, by the way. You don't have to actually run it there, because all the edges should have been accounted for at that point, unless you broke the code. But as you can see, even if we did look at it, we can see that there are no edges to look at, because everything is going to a visited node, because it's the last one, right? So, yep, that is it. We are done. So now we not only have our destination vertex and how to get there, we have how to get to every vertex in this graph in the most efficient way. But to figure that out, you don't look at the beginning, you look at the end. So you're like, where do you want to go? Well, I want to go to vertex 6. Okay, what's the shortest path? Well, it's going to take you 6 minutes to get there. And the way to actually traverse that is you go look at this parent, and then you draw that line. So you go here. Okay, and then from there it says go to 5. So you go to 5. And then from there it says go to 3. So you go to 3. And from here it says go to 0. So you go to 0, and there you go. So that's actually going to be your shortest path to get to the vertex. Okay? Let's say, for example, that you want to go to vertex 2. Well, if you want to go to vertex 2, you look over here, you're like, well, it's going to take you 5 minutes to get there. And to do that path, to do that efficient path, you have to go to 3. So go to 3. And then from there, you got to go to 0. So there you go. So as you can see, having that parent or having those breadcrumbs is going to allow you to actually know what the path to take is. So not just to know how long, it's not enough to know like, oh yeah, the shortest path is 10 minutes, but I'm not going to tell you what it is, because like, what's the point then? Yeah. So yeah, that's all there's to it, to the algorithm. Okay. Any questions? Go ahead and just drop them in the chat. Now what I'm going to do is I'm going to do the table version of this so that you can see it. Okay. So let me go ahead and draw another graph. Okay, these are way too big. Let's shrink them. I was going to do the same example that I had here to make sure that I don't mess it up. So let me actually add one more vertex here then. Okay. That looks nice, somewhat. I'm also missing a vertex on the bottom. There we go. Okay, I think I got all the edges labeled. Yep. Let's make that more clear that it's a 7. We have 14 to, yeah, okay. Let's put some identifiers to these. Okay, so now when you're doing this when you're coding this in a computer, you're going to do the exact same thing that I basically said earlier, but you know, it's nice to actually see how things are organized, or at least how you should organize them. You don't particularly have to do this. It's just advice of what tends to work. And that's basically to keep a data structure that allows you to essentially have an array of a object that has 4 sort of things associated to it. And those are the vertex, where we're going to call the key, which is going to be that weight, the parent, and then whether a vertex is visited or not. Okay, so let's actually put those in first. So we have a vertex, we have key, we have parent, and we have whether it's visited. Okay. 2, 3, 4, 5, 6, 7, 8. Not quite straight, but okay. Somewhat okay-ish. All right, so here's what we got. Let's see what we can do to. I think maybe we can. I want to maximize this. I think we can make the graph a little smaller. We'll be okay. Yeah, okay. That's okay. I think that's almost readable. You can always zoom in a little bit to see it, or do this. Okay. So let me go ahead and paste the algorithm. So now let me just give you the entire algorithm that I've been following, basically. So this is your Dijkstra shortest path. Okay. This is something you'll have to do on the test. I don't remember if I make you do the little like drawings like this, or I think sometimes what I do is I'll give you a bunch of, or I tell you to draw the table, so then you can just basically copy and paste it and just update it, because that'll be much faster than trying to draw the graph like 10 times and updating the numbers on it. Because I do want to see the steps of the relaxation. I don't want you to just show the final graph, because you could have done that without the algorithm, especially for a graph the size that you're doing on a test, right? So I think, yes, I either want you to draw the graphs. Here, I mean, I was doing it on the fly, but I want you to draw the graphs, and then every time you do relaxation, update the values so that I know the values that it works for a vertex. Or copy paste the table a bunch of times on Paint and just fill it out with the new values each time, and just copy paste when you replace it, which is a lot faster to do, I think. But the drawing could work too. So either or. Okay, so this is the algorithm. So let me go ahead and read it. Yeah, okay. So for all vertices, so we have a couple of variables. So we have u and v. So those are going to be just 2 vertices, u and v, like for example, edge vertex 1 and 2. And then w is weight. And so when we say for all vertex, for all vertex that are elements of graph G, where this vertex V visited is not equal to true, so where the vertex's visited field is not equal to true, so initialize this to false. Pick the smallest remaining key of this non-visited to true, non-set to true set of vertices, and then for that key, go ahead and do what was this E element? No, there exists. No, that's backward T. E edges, I think it is. For all edges that are elements. No. What is the uppercase E in this scenario? There are elements of U. I think it's edges actually, but I'm not sure. Hold on, check my notes. Let me check. Hold on. I don't want to say something that's wrong. Okay, I'm not sure what it means, but it must be edges because that's kind of what you have to do to this. Yeah. So let's just, I don't know why I use uppercase E for this, but it has to be edges. Okay. So for all edges that are basically coming out of U. Okay. So for all the outgoing edges that are coming out of U, so we have a vertex UV. If the weight of the key of U, so that vertex that is you're coming out of, plus the weight of that edge that you're looking at from U to V, if that value together added is less than what is currently set on the V key, and that vertex you're looking at is not visited, then update it. Okay, so this is basically doing the same thing that we were doing before. So I'll go again and say, so basically for all vertices that are in your graph, where visited is not set, where you haven't visited the vertex, get the smallest one of those, and then looking at that vertex, we're going to basically look at all of the edges going out of it. Okay, so that's this one here. And then for each of those edges, we're going to do this if statement check. And we're going to say, if adding together the current value that you have in that vertex, so that U vertex, plus the weight of the edge that you're looking at, so like 3 plus 1 or whatever, and that edge is going from U to V, if that value is smaller than what you currently have set on the key or the weight, the ongoing weight of V, and you haven't visited that vertex, because we don't want to update visited ones, then go ahead and update it with the this should be U here. Update it with the value that you have on U, which is where you're basically your new origin, plus the current weight. So you're taking basically what's here and adding it here. Okay, I don't know what some of the weird things are in this. Okay, so add those together, and that's your new shorter path. And make sure you also update the parent to be U, okay? Because that's the new origin that gives you that shorter path. When you finish going through all of these, so when you finish through all these edges, so this is basically together here. So when that's all done, then go ahead and mark U as having been visited, okay? And you only do this once. Okay, so that's the algorithm. Sorry that I had some issues with that. But hey, now it's fixed. All right. So let's just go ahead and do that. Okay, so we're going to start out. So again, we're going to say the 0 is the start. And again, it doesn't really matter what our destination is because this will compute it for everything. So we don't really need to set a destination. And even if we did visit that vertex, you don't want to... could you stop searching at that point? If you mark the vertex that you want it to be, if you're only computing this for one vertex and you never cared about the other ones, once you find the vertex and you actually get to mark it as visited because you had no other vertex that was like lower weight, so you actually went to that vertex and processed it, then you could stop the algorithm early, technically. So there's that. But either way, that doesn't usually happen because you can't trust it, right? You know, you got to think about the worst case scenario, which is that it'll be the last vertex you look at, which is kind of what happened with the first example. Okay, so let us begin by setting this to have no parent because it's a start. We're going to mark it as visited because it's going to be what we're going to first look at. And its current key is just going to be 0 because we are already there. And I'm not going to initialize all of these to infinity because I have to then erase it. But just imagine that all of these are set to infinity if they're blank. And the parents are set to like a question mark. And of course, they're set to false when visited. So the empty square means false, okay? So once you initialize this whole thing like that, then you're ready to start. So you're going to be looking at the edges. So we're going to be looking at the edges going out to 0, which are 2 of them. So we have going from 0 to 1 and from 0 to 7. So obviously that's always going to be better than infinity. So we are going to set these to say, okay, this is coming from 4. Or sorry, this has a weight of 4 and it's coming from 0. And then for 7, it has a weight of 8 and it's also coming from 0. Right? So at least we have 2 of them now. And then you're done. You already marked it as visited, so we're good to go. If you want me to go slower on this, we can plug in these numbers just to see it. So like when you're looking at the 1, what you're saying is if 0.key, which is basically 0, if that plus the weight from 0 to 1, which is equal to 4, so if 0 plus 4, if that is less than v.key, which currently has infinity, and visited is not equal to true, which is indeed not equal to true, then go ahead and replace 4 with infinity. So that's what's really happening in the computation. I'll do another one of those once we actually have more values. But yeah, so let's go to the next one. So you got to pick the smallest weight of the ones you have here. So we have 4 and 8, so we go with 4. So, or sorry, 4, sorry, I looked at the weight. We have to pick between 1 and 7. In this case, we are going to be looking at 1 because it has a weight of 4, right? So we're going to look at that. So this has 3 edges coming out of it. And so the way that we run this is we just go through each one and feed it to this. So let's go ahead and do 2 first. So 2 has infinity, so anything's better than infinity. So we're going to take the 4 that we have and we're going to add 8 to that. So that is going to be 12. And then that source is going to be 1, right? And also a good idea to remember is you can kind of keep a little arrow so you remember where you're currently at. Otherwise you'll screw this up pretty easily. So when you do that, you can say that you got one of the edges done. You don't look at this edge again because if you think about the formula, you know, it's saying v visited is not equal to true, but here it is equal to true, so that's why you don't touch it. You are going to look at this edge, and that edge is basically 11 plus 4. 11 plus 4 is 15. 15 is not less than 8, so even though you haven't marked it as visited, so this condition is okay, this condition is not okay, so that's why you don't update it. Okay, so that stays the same. So really there was only one thing you got to add, which was the 12, 1. So now we got 2 vertices to choose from, 2 and 7, but you go with the smallest one. So the smallest one is 7, so that is going to be the next thing to look at. So that one right there. And so let's move our little arrow. So again, I want to make sure I don't forget where we're looking at. Mark it as visited, so don't forget that either. And then go ahead and look at all the edges. So we have 4 edges. 2 of those are going to visited vertices. So we don't care about those. We won't compare them. But we do have this edge and this edge to look at. So let's go ahead and look at that one first. So we take the current value of the key, which is 8, and we're going to add that to the weight of the edge from 8 to 7, which is 7. And so basically 7 plus 8 is 15. So you go in and you put that in for vertex 8. So 15. Okay. And put the source as 7 because that's where you're at. All right. Next one is this one here. So for that one, we are going from edge 7 to 8. So that takes 8 plus the 1, which is a 9. 9 is less than infinity, so we are going to put that in, and we're going to put the source as vertex 7. Okay, so now we got 3 vertex we can choose from. Vertices 2, 6, and 8. 6 has the smallest value because it has a 9. So we will pick that one. We have to pick that one. It's not a choice at that point. So go ahead and mark it as visited, and go ahead and look at all of the edges that are coming out of it. And by the way, you know, when you're coding this, you're not looking at a pretty graph. You're looking at an adjacency matrix or a list. But you can just see, right, in an adjacency list, you can just go to that row and look at all the edges it's supposed to go to, and bam, you got the information. But in the adjacency matrix, you just, if you have your froms and your twos like that, then you just go and look again at the row and see where those numbers are not infinity, and now you know the set of weights you got to look at. So that's very trivial. So, you know, it's the same thing you do when you're doing depth first search and breadth first search to identify what edges are coming out. And of course, if you're doing a graph with pointers, then you just look at the array of pointers and see where they're going and what the weights are. So yeah, in this case, we have 7, 8, and 5 as the vertices, and all of them are not marked as, oh no, 7 is marked as visited, so we don't need to worry about that one. But we do have this one and this one to look at. So let's start with that one. Actually, no, let's start with 5 because 5 is definitely going to get updated, so we can just get that out of the way. So that one is going to be take the value of the key, so 9 plus the value of the weight, which is 2, and that's 11. So that means that 11 is less than infinity, so it gets updated. Put your right source, which is 6, and also just so I don't forget. Ooh, hold on. I'll move that. Stay. Let's put that at 5 so we know we're at 5. Okay. No, we're at 6. No, that was fine there. Okay. All right. The next one we are looking at is this edge. So we take the current value of 6, which is 9, and we're going to add 6 to that. 9 plus 6 is 15, which is actually the same that we have on 8, as you can see. However, this says less than, not less than or equal to, so therefore no update required. If you did update it, though, it wouldn't break particularly anything. It just means that, again, there might be more than one answer, possibly, for this. Okay, so... Yep, there's no need to update. So we're good. All right. Now we got 12. So we got 4 vertices we can choose from. 2, 5, 7, and 8, which have 12, 11. Wait, I said 7, not 7. Sorry. We have 2, 5, and 8 only to pick from. And of those, 5 has the smallest value because it has an 11. I'm going to put the arrow at the bottom now because it's starting to get crowded there. Okay, so mark it as visited and get going with it. So 5 has a lot of fresh edges we can look at. The one we don't need to look at is this one, so that's nice. All right, so let's just go with it. Let's go with 10. So 5 has an 11 right now, so we got to add 11 plus 10, which is 21. So 21 is going to be what we put here, and we put a source as 5. Then let's look at this one, 14. So going to 3, so that is going to be 11 plus 14 is 25. And that is going to be parent of 5. And now we get to look at the interesting one, which is this one. So that is going to be 11 plus 4. 11 plus 4 is 15. What do we currently have in 2? We have a 12. 15 is not less than 12, so no relaxation required. So that stays the same. Okay, now we got more things to choose from. We actually have all the remaining vertices to choose from, but we gotta pick the one smallest value, which is going to be 12 there, because the other ones have 25, 21, and 15. So yep, 12 is smallest. So that's vertex 2. Vertex 2 has 4 edges, of which edge going to 1 and edge going to 5 are already visited, so we don't need to worry about those. We just need to worry about the edges going from 2 to 8 and 2 to 3. So let's process those. Let's just go with 2 to 8 first. Going from 2 to 8 means that we have to take 12 plus the edge of the weight of the edge, which is 2. That's equal to, not obviously 24, but 14. Is 14 less than what we currently have in 8? Yes, it is, because 8 has a 15 in it. So we have found a new shorter path. We are going to perform relaxation. Bam, we have relaxed that, which means that this is no longer the parent. The parent is going to be what we're looking at here, which is a 2. So we basically found a shorter path by 1, and that path is via vertex 2. Very cool. All right, let's look at the other edge. Going from 2 to 3. So that's 12 plus 7. That's 19. Is 19 less than 25? Absolutely. So that means that we found also a shorter path here. So that's a relaxation that we are performing. It's no longer via parent 5, but via parent 2. So we have relaxed both of these vertices and their data. Very relaxing indeed. All right. Okay, we are done with that now. So now we got 3 to choose from, 19, 21, and 14. Do notice that you can't choose these ahead of time because of the relaxation, things might get out of order. So you can't like feed this to a queue and be like, oh, I know exactly what's going to happen next. No, you have to reevaluate all of the weights to see if any of the relaxations change which of the next vertices you're going to look at is. So you always have to recompute that. Make sure you don't try to like do some weird optimization where you're like, remember what the next thing to look at is, because those things can change out of order as they get relaxed. Okay, so looking at vertex 8, this might be an easy one because it's got 3 edges going out, and it's vertex 2, vertex 7, and vertex 6, and they all have already been visited, so no update required. Very nice. So we can just mark that as visited and we can move on. 19 and 21, 19 is smaller, so we have to go with vertex 3 next. Vertex 3. Vertex 3 has 3 edges, of which the ones at 2 and 5 we don't care about because those are already visited. So there's only one edge really that we need to look at, and that's this edge right there, going from 3 to 4. So we're going to take the key of that. So here, we'll do one slow one. We'll do one with the system down here. So what we need to compute is we need to know what U key is equal to. So we need to know U key. We need to know W U comma V. We need to know what V key is and what, I guess, V parent is technically. Okay, so let's compute all this stuff. So U in this case, well, let's say what U and V are in the first place. U is a start, so that's where we're at, so that's 3. And V is the edge we're looking at, which is, sorry, V is the vertex we're looking at to go to, so that's vertex 4. So then the U key is 3 dot key, so 3 dot key is 19. And then the weight going from U to V is the weight going from 3 to 4, which is a 9. The V key, currently what does 4 have? 4 has a 21. And who's the parent of 4 right now? 5. So now that we have all this data, we run the code. So we can say if u key plus wuv, so if 19 plus 9, which is equal to what, 28? If 28 is less than 21 and v visited is not equal to true, is v visited set to true right now? It is, what is v again for? It's not set to true. So this part of the if statement is good, but this part is not, because 28 is bigger than 21. So that's why you don't enter that. So yeah, so just thought I'd do one of these, actually plugging in the values, just so you know. But that's kind of what we're doing quickly here, okay? So in this case, there's no update to be done because 28 is not less than what we have before. So that means nothing really happens here. We can mark this as visited. Again, you don't technically need to look at the last vertex because of the optimization. Like, there's no edges to look at, but even if you did, you would see that there's no updates that happen. So we are done. All right, so what does this tell us? Well, what's the vertex we want to see? Let's just say we want to find out what the shortest path is to vertex 5. Well, let's look at vertex 5 here. Vertex 5 has a key value of 11, which means that the shortest path from your starting vertex, which is 0, that one you can't change. If you change, you got to recompute the whole thing again. So if we know that the shortest path is vertex from 0 to 5 is going to be 11 units, now we got to just figure out what that path actually is. So we look at the parent of 5, and that's 6. So that means go from 5 to 6. And then once you're here, go to 7. So 6 to 7. And from 7, go to 0. And that's it. That's your shortest path. So that's a 0, 7, and 5. 0, 7, 5. Or sorry, no. 0, 7, 6, 5. Right here. Okay? So that's how you look at that. And that's, again, the same algorithm we just did, but using a table, using it more systematically. This is literally how you would code it. There's no way you can get confused now if you just follow the basic coding and literally write this as actual code. Okay? Questions? When we do prims next week, it'll be more practice of kind of doing Dijkstra, because I said it's very, very similar. In fact, I'm going to use the exact same graph, but using Dijkstra. Sorry, by using cross goals. And you'll see that it looks very similar. In fact, so similar that you could make the mistake of using the wrong algorithm, which you don't want to. So you have to be careful about that. So I know that was very repetitive, but it's good to see a full example. Yeah, that's all I have. That's literally it. We just have one algorithm for the day, and we just did it. So it's not particularly a hard algorithm. You just have to you do it a couple of times to feel familiar with it. And then after that, it's just a matter of being very careful not to screw up numbers. It's very easy to copy a number wrong. And if you get a number wrong, that cascades into the rest of the code and bad things happen. How does Dijkstra work if you have one of those graphs where it looks like multiple graphs because they aren't connected? So Dijkstra is going to get you the shortest path to all of the vertices that it can reach. And for the ones that it cannot reach, because it can't reach them, those edges are going to remain as infinity. So like if you look at this value and like let's say that when you finish the algorithm, like let's say that this was left at infinity and you never visited it. If you ever get to a situation where you're trying to pick the next vertex to do, and the only options that are not visited are actually infinity, that is how you know that that specific vertex is unreachable. So like road is closed, or it's just simply through, like in Europe and you're in America and you're trying to drive across water. Okay, that would be the sign. So Dijkstra's shortest path can get you there if there is a way there. But if there isn't, it'll just say that there's infinity. Now, again, because the algorithm is only getting you the shortest path from a starting node, you know, it's only telling you like, okay, going from here to all other places, what the shortest path is. But if you're trying to compute the shortest path between like the two unconnected sections of the graph, then you would have to use those as your origins and recompute the whole thing over. And in that case, you'd get the shortest path of that region, and everything else here would be infinity because it's unreachable by that sort of island per se. Fun fact, if anybody wants to look further, there is an A-star algorithm, which is like Dijkstra's shortest path, but optimized to make it faster. What it does is it uses a heuristic, and that heuristic is basically kind of like an educated computer science-y guess. I'll talk more about heuristics in that one bonus video if you check it out. But ultimately, it uses, one of the heuristics to use is, for example, coordinate. So like, if you know that your destination is in one direction, then you tend to try to go in that direction and just kind of compute that primarily as like, well, you know, if my objective is to go like from like, let's say from like New York to like Florida, more than likely I should drive south because like it's south of New York. So when you're computing a graph for Dijkstra's on the map, the way it typically tends to work is like, it's like a growing circle. And finally, when that destination gets engulfed in that, then you start to find a possible shortest path. But you don't really confirm it until you get like an even bigger graph. And then finally, it's like, well, that's the shortest path. With a heuristic algorithm, you might just check that section of the map. Actually, no, that's misleading. Maybe more like that. And so heuristics can really optimize this, but it's a heuristic. So like, you know, let's say that there's just this massive wall, like I don't know. Let's say you're trying to go to Mexico and like you're trying to go to like San Diego, but like there's a wall right between two countries, and like there's border entries that you can go in and out, but like, you know, if you have a situation like where like, let's say you have the wall and you're here and you want to go here, and then there's an entry point there, the heuristic will try to make you check this way first until it finally sees the gap, and then it'll go this way. Whereas Dijkstra would have probably done something more like this, and actually may have finished before. May still not be as efficient. But it's called the concave problem or something, where like heuristics may get confused when there's this weird shapes like that, such as a wall or something. So, yeah. If you have claim, can we also claim? Yes. So if you have additional points, you can keep claiming more points. So yes, you're welcome to claim that. Just make sure you. Anybody who claimed points today, make sure you send me a message with your names, the class you're in, and your Twitch name. Your real name and your Twitch name and the class you're in. Okay. I thought I'd just bring up the heuristic stuff since we had some time. I didn't see any more questions in there. So, cool. Remember, the last day to claim points is it's a week from today. So, I don't want people to tell me like, oh, I forgot to claim the coins, because you have no way of claiming it unless I'm live. So after I stop streaming on Monday, that's kind of it. You have to like, so yeah. How would we apply Dijkstra to the grid assignment? So every single unit in the grid is a vertex. You think of it that way, and then you just do Dijkstra. So every vertex has potentially 4 edges coming out of it. Up, down, left, and right. Or if you want to do it diagonal too, you could do that. But I think you're better off doing it up, down, left, and right. Although actually diagonal could work. Diagonal will work too, but yeah, it should make it harder. Just you get to be careful with diagonals, because when you walls, you can teleport across a wall and buggy things happen. Smells weird. I'm not sure about the Office Excel thing, because I don't really know how they did that. Will test 2 open up so we can see what we got correct? I think it got posted, but I don't know. Maybe I'm thinking of the 202 class. I know that one of the midterms got posted today. I don't know if it was the 202 or the 302 midterm, but I did see an email about that. So if you haven't seen it, then it's probably the 202 one. Oh, did they get posted? Okay. Grade posted, not questions. Well, if you have a specific question about a question, just ask the TA and he can probably pull it up and show you. Well, coding an aimbot is probably much easier than coding a normal non-aimbot, because literally when you have a line of sight on the target, you make it shoot. So it's literally more like a trigger bot. It's like the moment it goes in its line of sight, it shoots immediately. So it would be much harder to make it more human with there's a delay and things. So you're all technically coding aimbots and wall hacks in a way, because you could probably, yeah. Your bot can see where the objective is, even though it can't see it physically. It knows where it's at, so it can walk in that direction. So yeah, they all have wall hacks and aimbots. All right then. It smells like there's a gas leak or something. I'm gonna go and inspect that probably during my break between both classes, because it does smell strange. When I implemented Dijkstra, that table, I showed the numbers when I printed it out, and that was pretty cool to see. It is nice. It is nice to see actually a practical use of Dijkstra, like Google Maps and just navigation in general. I like it. We got to use all the app that you guys tested, the AirNav app, that was using Dijkstra to be able to compute the arrows. So Dijkstra is very popular. It's very cool. Very nice thing. So it's one of those algorithms. And by the way, they love to use it on interviews. They love to use these graphing problems in interviews. So you got to make sure you got them down, or you refresh them before you go do some interview for a computer, for a coding company or something. They'll hide them. They won't tell you. It's like, oh, do Dijkstra. They'll do like some sort of problem that requires shortest path. And in algorithm class, you're going to learn like 10 different shortest path algorithms, like Bellman-Ford and whatnot. Negative edges. Dijkstra will not work with negative edges. You try to do it with negative edges and the whole thing breaks. So just FYI. But yeah, the shortest path problem is very popular when it comes to interviews. So Dijkstra is just like the nice and easy one to do. But you'll get to see it a lot more in 477. So this is not the last time that you'll see Dijkstra. All right then. Well, that is all I have for today. There is class on Wednesday. I mean, I do record it, so if you are going to do an early holiday break, then that's okay. But you know, if not, I will be here teaching you about minimum spanning trees. So until then, see ya. Have a great rest of your Monday.